So, previously we saw about the projections. So you remember you had your space E, which can be written as the direct sum of two subspaces F and G. So that's important. E is equal to the direct sum of F and G. So you have that any x in E can be uniquely written as x is equal to x1 plus x2. And I had taken this example where you had one of the spaces, sorry, f could be, for instance, if you are in R3, f could be a plane, so with its own basis, and you could say that you had a third direction, okay? So let's call this space G, so that any item X that belongs to R3 could be written uniquely as one item X1 in F and one item X2 in G. Okay, and the projection, it was taking this component, the x1 component. Now with the linear symmetry, we are going to describe the linear symmetry as we're taking the difference of x1 minus x2. So what does it give us really when we take this? So we take the same x1 and we take minus x2. Minus x2 is going to go here. So what do we get? We are here, we're about here. That would be the symmetry, the symmetric of point X with respect to F along the direction G. Okay, so I keep the x1 component and I take the opposite of the x2 component, right? So S of x is really defined as we keep x1 and we subtract and we add the opposite, we subtract the x2 component so that we land exactly on the other side of the space F. Well, that's one way to see that. If I did sort of the contrary, if I took the symmetric with respect to G along the direction F, I would take the opposite of x1. That would be, let's say, minus x1 and same x2. Okay, so this would be the symmetric with respect to G of x. That would land here. Okay, you say I land on the other side of my space. That's one way to see that. All right. So what do we have in that? So that's the definition. So one way to do something similar as what we had previously is that the space F, the one for which we take the symmetry with respect which we take the symmetry is going to be the kernel of S minus the identity, and the other space G is going to be the kernels of S plus identity. And of course, if you describe the space E, it's going to be the direct sum of S minus identity plus the kernel of S minus identity and the kernel of S plus identity. Okay, and you have this remark that indeed if X belongs to the kernel of S minus the identity, it means that S minus the identity of X is equal to 0, so that S of X is equal to X. Okay, and similarly, that so that, and what does it mean? It means that anything that belongs to this space F here is not going to move with respect to this symmetry. So the symmetric of anything that is already on that in that space is itself. That's what it means. Whereas if you take anything on the other space, its symmetric is just going to be its opposite. Okay, that's what we get here. right? And so the same way we could show that a map was a projection by saying, well, it's equivalent to have the map composed with itself is equal to itself. So P composed with P is equal to P. That was for projections. For symmetry, we had something very similar. We have that if you compose twice the symmetry, you're back where you started. Okay, with the symmetry you took X, you took the symmetric, you went here, and if you do the symmetric of that one, you're back where you started. Okay, so that's the idea of this linear symmetry. Okay. So finally, practically, if you have a linear map that is represented by a matrix and you want to know whether it is a linear symmetry, well, you just have to take the square of the map, and if it's equal to the identity, then you know you have a linear symmetry. And then if you want to find the important spaces, the spaces F and G of this symmetry, then you have to find the corresponding kernels of S, your map minus the identity, your map plus the identity. Okay.